Good morning. Welcome to the next lecture of energy conservation and waste heat recovery. Today, what we are going to discuss is a topic called heat pump. Okay. So, what is a heat pump? Let us first recap. This is something that you may have studied as part of your applied thermodynamics. So, we will first start with what a heat pump is, and then look at applications as to how a heat pump can be used in the context of our course, which is waste heat recovery. Okay. So, let us first talk about a heat pump and what it is. Let us come to this figure over here on the PowerPoint. A heat pump, if you recall, is pretty much the cycle, if you look at it, is the same as that of a refrigerator. Okay, in the sense that you have a evaporator, you have a compressor, you have a condenser, and you have an expansion valve. But for the time being, let us leave that out and just look at the heat pump as just as a system. What heat pump does is, it is able to move heat or transfer heat from a temperature which is from a temperature T2 which is lower to a temperature T1 which is higher. Okay. So, typically now second law of thermodynamics states that is not possible unless we have some external energy being supplied to the system or external work being done on the system, right. So, therefore, this is not, so as a result it is not possible, spontaneously it is not possible. So, we have to do external work on the system, and that external work is actually the compressor work that is done on the system, and which enables us to move heat or to transfer heat from a temperature which is lower to a temperature which is higher, or in other words transfer heat across an adverse temperature gradient. It is possible only because we supply external work on the system. Okay. So, this is how, again the same schematic as we saw over in this PowerPoint slide is over here as well. So, T2 is definitely lower than that of T1. So, let us make that very clear, T2 is lower than T1. So, this movement of Q2 from T2 being extracted from Q2 and rejected to T1, that would not have been possible unless we did this external work W. Okay. So, what is the COP? Its coefficient of performance. Let us recall that, and it is defined as the desirable effect to the input that you have to give to the system. So, what is the desirable effect here? Okay. So, the desirable effect for a heat pump is Q1. Okay. The amount of thermal energy that I have, which I can use at an elevated temperature. Okay. I wanted to generate thermal energy at a high temperature, so which is a higher grade of energy, and so Q1 is my desired effect. And what is the penalty that I put in terms of the energy that I have to spend in order to get that? That is W. Okay. So, for a heat pump, this is the definition. For a refrigerator which has the same components and works in the same principle, the COP of a refrigerator, the desired effect is different. The desired effect is the amount of heat that I can extract from the cold temperature to maintain it at that lower temperature. So, what is the amount of heat that I have to extract and reject to the outside or reject to the high temperature? So, for a refrigerator, my desired effect is Q2. Okay. The heat that I supply to the evaporator, and of course, the penalty paid or the work done is the same. Clear? So, now from first law of thermodynamics, I can conclude that since Q1 is equal to Q2 plus W, I can show that the COP of a heat pump is 1 plus the COP of a refrigerator. Okay. So, COP of a heat pump is always greater than 1. All right. So, this is just from mathematics we are saying it is always greater than 1, it better be very much greater than 1 if we are going to design a good heat pump. All right. So, this is from thermodynamics point of view, thermodynamic recap of what is heat pump. Now, what are we going to use it in the context of waste heat recovery is the next question. So, in the context of waste heat recovery, what we will do is we are going to use a heat pump which of course needs additional input of energy in the form of mechanical work like in a compressor. We are going to use a heat pump to upgrade energy or to upgrade thermal energy which I have at my disposal. Okay. What do I mean by upgrade? Let us say I have thermal energy available to me at a low temperature, let us say at ambient, let us say at 30 degrees centigrade, but I need the thermal energy at a high temperature, let us say at 80 degrees centigrade. So, how do I upgrade thermal energy from 30 degrees to 80 degrees? Heat pump is one way by which I can do. Of course, it does not come for free, I have to put in additional energy, external energy to it. Clear? So, let us look at the next slide, which is what we are saying here. What is the value proposition of a heat pump? The heat pump is used for upgradation of low grade or reject heat. So, let us say low grade heat at 35 degrees can be upgraded to deliver heat at 80 degrees centigrade. This is 35 and 80 are just two numbers that I have picked. Okay. So, essentially at a low temperature to higher temperature. So, that is the value proposition. So, how do I do this? Yeah. And or why do I do this in the first place? It increases the quality of energy, we know that, right. The thermal energy at a higher temperature is at higher grade compared to thermal energy available at a lower temperature. Clear? So, that is what I am showing here, that is what I want to do. I want to upgrade the energy, which means improve the quality of the energy that is available to me. Okay. And again I have to spend something in order to do that. Clear? So, that is why I said at the cost of external work to the system. It is heat pump actually, if you again look at the cycle, what happens? I am removing heat from the lower temperature using the evaporator. Okay. So, I am cooling at the evaporator region, it results in cooling of the surroundings, and at the condenser I reject heat to the higher temperature, okay, which is the amount of additional heat that I get, that is the upgradation that we are talking about. So, if I have an application where I need both heating as well as cooling, this is a very ideal scenario, right. So, if I need simultaneous heating and cooling, or even if it is not simultaneous, it can be at different points of time or different points in space, heat pump is very ideal. Clear? Okay. So, for example, year round air conditioning, let us think about a place with extreme climate, let us say Delhi or Rajasthan. It gets very hot in summer, it gets very cold in winter. So, I would need air conditioning during the summer months, and I would need heating, room heating during the winter months. I am talking about residential use right now. So, it is possible to use a heat pump. Let us say I use the ambient air itself and I use the heat pump so that I can get air conditioning during summer using the same setup with a slight modification, using primarily the same equipments. I can have heating in summer, I can have heating in winter and cooling in summer. All right. So, the last point I want to make over here is the capital cost, in the sense is not very different compared to an AC system, okay, because here also I primarily need more or less the same equipments. I need a compressor, I need an expansion valve, and I need two heat exchangers which will work as evaporator and condenser. Okay. So, I can have an AC with electric heaters and do the same thing, but the energy cost in this case will be much lower. The capital cost is the same, but the energy cost will be lower if we use heat pumps. Okay. Keep that in mind. So, with that I will say that what is the heat pump capacity and working fluid. Okay. So, what is the capacity going to depend on? It is going to depend on what is written on the slide. It is going to depend on the cooling load on the evaporator. So, let us say I am using it for cooling in summer. What is the amount of heat that I need to reject? So, in our ACs we call that 1 ton of refrigeration, 1.5 ton of refrigeration. So, similarly what is the cooling load on the refrigerator in the evaporator, right? The air volume and air change requirement, heating load on the condenser. Okay, if you are using it as a heat pump and the heating is my primary goal, then what is the heating load that I need? And of course, last but not the least, the capital cost. Okay, what is the how big a compressor I need? What is the rating of the compressor? How big of an heat exchanger do I need at the evaporator, at the condenser? What kind of an expansion valve would I use, and so on. Okay, the working fluid typically can be our refrigerants. So, R11, R12, R21, R114 and all these things are well known to us. Azeotropic mixtures of 2 or more of these fluids is also used as heat pump fluids. Okay. So, with that background, let us now look at one application where, not application, this is more of a generic, I would say, how do we use heat pump. So, heat pump, if we think about 2 scenarios. The first one, as I am showing in the slide, in the first case I am saying that I have a process stream and in one place I need heating, in another place I need cooling. Okay. So, look at here, heating and cooling required at different places in the same process. Okay. So, I have a hot feed coming out, I have a hot feed available with me. Okay. And my final product is also needed to be heated, but there is an intermediate process which needs to happen at a lower temperature. Okay. So, then what will I do? So, I will use a heat pump where I will first have the hot feed go over the evaporator. Okay. In the evaporator what happens? The refrigerant evaporates or boils, goes from a liquid state to the vapor state. So, therefore, what happens? It absorbs heat and the hot feed becomes cold. So, as it comes to this process over here, it is at a lower temperature, and it is lower temperature, sufficiently low so that the process can happen at that temperature. So, the process then takes place, very nice, the input is lower temperature, the output is also at low temperature, but finally when it goes to the next stage, the product that came out of the process needs to be heated up. So, in that case what I will do is I will let it pass over the condenser. In the condenser what happens? The refrigerant which is coming out of the compressor at a higher pressure condenses. As it condenses, it rejects heat, and that heat is picked up by this product that is coming out of the process, and therefore, the output from the condenser will be hot product which can now go to the next stage. Okay. So, this is a process where at one point I need a low temperature, but later on in the next process I need a high temperature. So, what do? I use a heat pump. I first use the evaporator to bring down the temperature, and which provides the input to the process which needs to happen at a low temperature, and then the product of the process which is at a low temperature needs to be heated up for the next stage, and that is done at the condenser. Clear? And again, just let us recap what happens in the heat pump, the same as the refrigeration cycle. You have a refrigerant which is at a low temperature and pressure at the inlet of the compressor. It is compressed by the compressor, where it goes up to a higher pressure and therefore at a higher temperature, and the higher temperature it condenses and rejects heat and becomes liquid at the higher pressure still, and then you use an expansion valve where there is an isenthalpic expansion, where the liquid condensate or the liquid refrigerant at the high pressure is suddenly brought down through this expansion valve to a low pressure where it is typically still liquid or at the two phase region with low quality, and then it passes to the evaporator where it boils and becomes vapor, and as it boils and becomes vapor it extracts or absorbs heat and thereby cooling the ambient of the evaporator, right, before, and then it comes to the compressor and the cycle repeats. All right. The second one are two processes, okay, two process streams, not the same process stream, two process streams, one needs heating, the other needs cooling. So here what happens is the same thing, you have two process feeds, one over here. So where you need chilling, you let that process stream go through the evaporator, and where you need heating, you let that process stream go through the condenser. Okay. So the first feed as it comes out is chilled, the second feed as it comes down is heated. Why? Because the refrigerant has rejected heat and condensed, and thereby heating up this feed in the condenser. Over here the refrigerant at the low pressure has converted from liquid to vapor, and while doing so it has absorbed heat from this feed 1, if we call it so, and as a result the feed has lost heat and it has become chilled or cold. Okay. So you can appreciate the fact that how a heat pump can be used in case of a in a certain process where you may require in the same process stream heating at one place, cooling at another place, or two different process streams, one needing heating, the other needing cooling. Okay. The source of heat in this case is still waste heat, but not at sufficiently high temperature, and that is why we can use for in the context of waste heat recovery, the waste heat that we have available at our disposal is not at sufficiently high temperature, and the heat pump is used to upgrade that. Clear? So let us look at an application like that. We will look at an air heat pump where which we can use for cooling during summer or heating during winter and heating during winter. Okay. This is typically ideal for a residential and small enterprise, and let us see how it works. Okay. So I will draw a picture over here where let us say that during summer I need cooling, right. So I will say this is summer. Okay. So I have a room which I need to cool down, okay, and I have another outside unit where I will do something. I am not, I will see what we will do over there, and say this is my overall control volume. Okay. So now let us draw the components of the heat pump first. Okay. This is a heat exchanger. Okay. This is an expansion valve. Let me denote it in this manner. This is one more heat exchanger which is placed in the room, and this is how it goes up. Now what I will do is I will draw a compressor over here denoted by C prime. Again let me write C prime is compressor, EV is expansion valve. Okay. So this is where a certain unit becomes very important, and it is called a four-way switch. Okay. So this is a four-way switch, and let us say this is one position of the switch. So what happens here is in one case I am going to draw this one, this compressor. Okay. So, I have drawn it in this manner, and let me put some arrows over here. Okay. Now, this is the room that I want to cool. So, therefore, what happens? What do I have in summer months? I have ambient air. So, ambient air is more or less at an elevated temperature. So, this is my ambient air coming over here, and then I will let it pass through over here. Okay. And what leaves from here is cold air. Why? Because I am operating this heat pump in such a manner that this heat exchanger inside my room is the evaporator. Let me put a fan also, so that it helps in blowing the air and gives rise to forced convection. So, this acts as the evaporator. Clear? So, the refrigerant liquid at the low pressure coming out of the expansion valve flows through this heat exchanger, where it absorbs heat from the hot ambient air that is coming in, thereby cooling this ambient air to a low temperature, and this then goes to the room. Clear? And then of course, the refrigerant vapor goes to the compressor, where it is compressed, comes out as high temperature, high pressure vapor, where again the ambient air flows over it and comes out as even higher temperature. Clear? You can use this heat for something else also. Okay. So, this is hot air, this is cooled air, and this is ambient air, which is at an elevated temperature in summer months. Yeah. So, this is how it works. So, this is nothing different, not very different from what we have for in a regular air conditioning unit. Now, the trick over here is the following. In the winter months, what happens is the following. So, again let me draw the same thing over here. What happens is the switch is going to change its position. So, let me draw it again. I apologize for doing it once more, but I think for our understanding it will help if we go a little slow. Okay. That is the reason I am not showing it in a PowerPoint, and rather drawing it over here. So, it is the same thing now. This is during winter. Let me draw the same expansion valve comes out, and it goes up like this. I have the compressor over here again, C prime, and I have the two ways, the 4-way switch also over here, but in this case now the position of the switch is changed. So, if the position of the switch is changed, this is what happens to the flow stream. Okay. So, here this flow stream goes like this, and from the compressor it comes down in this manner. So, this is the input to the compressor, because of switch is changed. So, the input to the compressor, the output comes through this, the flow is reversed, and this is how it happens. So, now what happens? During winter, my outlet temperature is cold. So, again let me draw a fan over here. But then what happens is this ambient air starts getting heated and comes out like this. Okay. So, this is heated air, and over here what comes out is even chilled air. Okay. So, this is chilled air. Okay. So, this is how it is. So, what has happened essentially, this is during winter. So, let us compare the two. Depending on, this was summer. So, depending on the position, the heat exchanger inside the room acted as the evaporator. What I did was I switched this so that the streams entering the compressor and exiting the compressor are changed, and essentially what I have done is now the direction of the refrigerant loop is reversed, and the over here the heat exchanger which acted as evaporator during summer now will act as the condenser. Clear? So, let me write it down again here with the maybe the green ink. So, this is the condenser in winter, and this was the evaporator in summer. Last thing I want to point it out, this chilled air also has application. I mean, this chilled air can be used for, let us say, water cooler. Let us say if it is a small industrial enterprise, you can use this chilled air for some of your processes which needs chilling. So, for example, let us say in a dairy farm, you need to keep the dairy products in a chilled environment, you can do that. Let us say in an injection molding unit or plant, you can use this chilled air to cool down the molds or the molten plastic, to cool it down and take form. And similarly, over here, when you get in summer months, if you get hot air, and if you are again talking about a small industrial enterprise, hot air has lots of applications. If nothing else, this hot air can be used for a vapor absorption refrigeration cycle, which you know, which you have studied. This is, I have upgraded the heat energy from ambient, which was probably at around, let us say Delhi summer will be 40-45 degrees centigrade. I can upgrade it to almost 70-80 degrees centigrade. Use this for something useful, for waste heat recovery. Clear? So, this is how a heat pump is an air to air reversible heat pump, okay, which is what I started by showing over here. Year round air conditioning using an air to air heat pump, we can achieve cooling during summer, heating during winter. During summer, when we are cooling the room, we are also getting a heated air stream which can be used for various other purposes. And similarly, during winter, when you are heating the room, we are also getting in the evaporator section chilled air which can have several other applications, right. Okay. So, for this lecture we will stop here, and we will continue our discussion on heat pumps in the next lecture. Thank you very much.